2000, Honda Motor Company came and said, Chris, we would like for you to lead the design and construction of a really big project in Alabama. It was important for our state. And they said the first phase of the project was a training facility, and it needed to be open 1 year before the big factory was open. And so we had our first meeting. It was a kickoff meeting. There was no official program. There was no equipment list. There was really not much more than the Japanese leadership saying, we want a world-class facility to train 4,000 workers in 200-person shifts, and we want it 9 months from yesterday. And we, of course, because that was the type of people we are, we said, yeah, that sounds like a great amount of fun. We will take that on, and we did. Fast forward to our second meeting, and we learned 3 things about the Japanese and their leadership style. Number 1 was they offered all of Honda's resources to help us help them be successful. It's really important. I don't think we would have gotten there without that notion. The second thing that they offered us or that revealed to us was that I think this was not the first time they had asked their trade partners to solve a really hard problem. And the third one, which was the most important, was there was not a chance in the world that they weren't going to open this thing 9 months from last week. And so fast forward 6 weeks and we've broken ground. Imagine that. 6 weeks later, we have broken ground on a 1,000-acre site, and we are moving dirt and getting ready for foundations. And at this point, if it wasn't earlier, it is abundantly clear that unlike Japanese automotive industry, the American design and construction world had failed to invest in the research and development necessary to begin to think about ways that you could deliver a high-quality space in compressed schedules. And so from that, a group of architects and builders and engineers, we got together and we began thinking about what a framework could be that would allow us to fix that. And we came up with a goal. It was our man on the moon notion, and it was 2 by 2 by 2. And we wanted to create a framework that would allow us to yield twice the quality of traditional construction measured by objective benchmark like energy efficiency, life cycle cost, and some soft ones about patient experience, about clinical efficacy and other pieces. The second part was that we wanted to deliver these things at twice the speed of a traditional delivery, and we want to measure that by an objective criteria of a permit to a certificate of occupancy. And finally, we wanted to do this in such a way that we delivered to the owner twice the value or half the cost. And if we could do this, we felt like we would be relevant in a world of clutter. An example of how you get there is interesting, because if it were 2 times 2 times 2 and that equaled 8 and it was 8% change, then there are a lot of ways that you would get there with value engineering, maybe change the specifications, maybe competitively bid it. But if you realize that that's an 8-fold increase, that's an 800% delta, then you're not going to get there by thinking conventionally. And so this thing is the normal. We have an idea, and it goes to design, schematic designs, and then it's modeled in 3 dimensions, and it goes to CDs and subcontracts, and it goes through submit, and it goes back to the architect, and it moves all the way down, and ultimately, down here, Brian gets to use his building. Conventional wisdom says, why don't we just clean up? Why don't we use technology and tighten up the spaces between each one of those things? And if we do that, we'll save maybe 1 or 2%. So I'm still about 700%, 798% short of the goal. And so we have to think about it differently. And we say, what if we go from model, from BIM, to G-code, to fabrication, and it allows us not to just simplify this piece, but it eliminates it, and we take that approach to hundreds of things that we work on, right? So we want to go from a thoughtful building information model to fabrication G-code, which allows us to work in a different way fundamentally. That requires technology at a level that really didn't exist in our industry. And this graph simply is a platform, cloud-based platform, think of it as an ERP, that takes raw materials and organizes it with manufacturing constraints regulatory constraints. It finds best-in-class manufacturers. It makes standard products. Those products are then distributed through a secure web portal, cloud-based. Really simple, very beginning basic of how you use technology to begin to change the paradigm. All of that needs a framework to tie it around. And the framework that Michael suggested in the beginning is design, manufacture, construct. Design, manufacture, construct is ridiculously simple. We're from Alabama. It says, we're going to teach a legion of designers how to leverage manufacturing productivity so construction's simple. If we can do that, we'll make a difference. Here are the three things that we have to focus on. We have to create systems instead of the brute force that we use to accomplish the Honda building to make repeatable processes. Those repeatable processes are what we use to achieve quality in a dwindling skilled labor market. And finally, we have to do that with the speed to market that affords us the ability to invest in the tooling and the research and development in order to have cash to throw this party. So this is a typical North American job site. We've got 4 guys watching the 5th guy eat a ham sandwich surrounded by the man-method material waste inherent to any job site. And if you imagine this construction fence that goes around every project is this black box. And this black box is the job, your hospital, and these are the men and women, the methods and the materials that it takes to build it, that what we're gonna do with design, manufacture, construct, in its early baby step, is we're gonna lasso a critical mass, and we're gonna pluck it out. Something magical happens in both places. Over here, we take 800 parts, and we organize them into a lean facility. The lean facility takes 13 integrated trades and creates many parts a day, hundreds of parts a week, thousands of parts per year. But something magical happens over here that's subtle. And this is the one where the general contractor now has an opportunity that heretofore they did not have. And that is to use oxygen that they never had before, right? There's 25% less people, less complexity, less material, less regulatory that's happening here. And when that plucks out, this is a leverage that someone gets to touch. But these pieces, even if they don't work, and they come in with a density that changes the gravitational orbits of all the subtrades around that, and you get a leveraging effect just by doing it. So 40, this is low, but the 25% that was removed becomes 40%. So this is Design, Manufacture, Construct version 1, and we have HCA as our wonderful case study to do it. This has been a 5-year program. We've worked in 20 states, hundreds of projects. It's exciting. This is what it looks like. They came to us. This is another one of my spaghetti diagrams. I apologize. But this represents the complexity of the building types that Brian's company has at HCA. They don't just have one type. They have dozens of types, greenfield projects, vertical expansions, clinical, outpatient, MOBs, et cetera. And they'll tell you that they have a robust design standard, the best in the business. And so we mapped it out. This was one that we showed. Oh, well, look, the departments that are colored here are, you have a couple of extra ones, right? There's a little bit of complexity in that. But then when we take it from the department level to the unit level, to the granular level, there is an explosion of variety. A patient room is not a patient room anymore. There are dozens and dozens of standard patient rooms. There are dozens and dozens of exam rooms. There are dozens and dozens of general surgery rooms. These are not standards yet. There are variations that prevent us from advancing it. So we said, what if we could go from here to here? We could make 9 standard parts. Parenthetically, that's now about 45. We could use those standard parts to populate these departments. We could use these departments to populate these building types. We would make a difference. That diagram woke up that department in a way like nothing else that we've shown them has. That was the step 1. From that removal of variation, we have a new opportunity emerge. And that is the idea of standardization for the first time, meaningful standardization. When I have 400 rooms that I'm trying to standardize, I go apoplectic. There's no chance I can begin to think in that level of complexity. But I can standardize a finite set of 9 pieces, which when you add ADA and left hand and right hand, it quadruples, but still a finite amount. So standardization is the next step. This is exciting for me. I believe that if they ever write this story, this picture, which was Innovation Memorandum 21, Greg Stein published in, say, 2014. But this is the one where he said, these are our parts. We work in 38 states. We have several hundred hospitals, but these are our standard parts. Our standard bathrooms, BPR01, it now has a model number. It's a SKU. There's a head wall for med-surg. There is an overhead ceiling rack. There are surgical racks. There are a series of standard parts that defined their standards, not as a design standard, but as an intelligent standard, a manufacturable SKU that could begin to change the supply chain systemically. So these pieces are really interesting, and interchangeable parts become the ability to make a programmatic level decision instead of a project level decision. And these pieces are installed routinely from Miami to Las Vegas. Cost is always something that's interesting. And so we benchmark the standard stick built of these pieces. We kind of know what that is in terms of cost. Some of this is redacted. And we look at design, manufacture, construct. What are these parts, these standard interchangeable parts in the beginning? And unfortunately, there was a premium. So most of you owners in the room right now, eyes roll back in your head and you go, I knew it. It wasn't going to work. And you're right, if you stop around here at the wrong point. But if you have the stomach that HCA had, then you push through it and you know that it has a promise at another spot. And this promise is one that happens really, really rapidly at scale. Once you amortize the fixed cost of a plant, of the engineering that's associated with the toolings, then the cost of this becomes incremental and not linear. And so the red represents the potential gain. But if you remember, we only took 25% out. So what the problem is there's not enough stuff in the red and there's way too much stuff in the black, and we have to begin to think about design, manufacture, construct version 2 so that we can get more from the black into the red. And I probably should change the wording of those. Case study, freestanding emergency department. Why? One is it's small, it's 12,000 square feet. The other one is it's acute care. That means it has trauma and CT and X-ray and lab. It is an acute facility, not a business occupancy. It has med gas and the complexities attendant to a small hospital, but it's not big. And so we can learn something. And what we learned when we do this is that the way we were making the parts in version 1 was a lot the way they were making the P-39 Air Cobra. It is piece by piece. And what we wanted to do is rethink that to a thing that Boeing has adopted in the 21st century to make the 787 Airbus, which is called chunking. Chunking is where I take best-in-class manufacturers around the world, and I make the biggest thing I can do, and I make them put all of the stuff that's needed into it so that it looks like this. It's a painted, completed piece, and it's coming from 12 countries. And those pieces then go to Charleston, where they're assembled. And Boeing is the OEM, but imagine this is what the construction site looks like. Radically different than that image that we saw where the 4 guys are watching the 5th eat the ham sandwich. Our chunk is called an Uber. And an Uber is not to be confused with ride sharing. It is the largest DOT transport. It's 15 feet wide, 15 feet tall, nominally 60 feet long. It's a red iron structural steel piece that can be stacked 30 stories high. In it, in that universal frame, is a lot of complexity. We can put a central energy plant in it. We can put a CT. We can put a lab. We can put X-ray. We can put a patient room. We can put a dietary in it. We can put any number of things, and we're adding things all the time. This is the freestanding ED that we started with. It has eight Ubers. The red represents those big modules. The space in between represents smaller modules that sit in place. The red represents the exterior cladding that we add to it. So here's the way that works. We go to the job site, we pour the foundation, it's a stem wall. We add the Uber modules, which represents about 50% of the overall complexity of that building. We add the flat pack steel. We put the exterior siding on. By week 6, we're dried in and conditioned. We put the other modules in, the overhead MEP racks, and then we begin to analyze. Our analyzing of the data shows that 1, 2, 3, 4, 5 of these were our first group. Our design time went from over a year for the first one. Imagine we're not making a single project, we're really making a platform, to half of that time for the second, still learning a lot, to a third of it, to where we're producing these things in 45 days pretty nicely. A lot of gains on design. There's a corollary to cost with that time. Manufacturing, our COO, Laura, took over 100 days to build the first batch of 8. It was pretty painful to watch. But her second one was a lot faster. And her third one was faster still. And now she's making one, need to check the numbers, but around 25 days to produce a whole set of the components that it takes to make one of these buildings. Pretty exciting. And then you can see why I love construction so much. We have improved not one whit. We have now done it 5 times, not a single improvement. In fact, if I look at the micro graph up there, it got worse. We regroup and we decide, how do we fix that aspect of it? We're going to take it 2 ways. Number 1 is we're going to shift more from construction to manufacturing, which means that we have to move it all the way back to design. And the other one is we're going to work at getting better at being a contractor. And so HCA was our next group of 5 projects, and this is underway now. And instead of doing 8 modules, we did 15 modules. It was a redesign, really powerful, and we began to see that the design, we've done the 5, gets better, manufacturing gets better, and construction, we're about right here now. We get to see what happens on this next one. So these should be dotted because this is what we'll show next year. Did it actually get better? When this happens, we will have solved the Gordian, or unraveled the Gordian knot of higher quality at a faster rate at the same or lower cost. The next thing is design manufacture version 3, which is the real holy grail of what we're working on. It is how do we deal with acute care at a significant level. This represents a patient room, a universal patient room. It has a lot of complexity in it. Each one of those parts is going to ultimately be best-in-class materials. It becomes the iPhone of patient care. It works in an Uber module. The Uber module can stack 30 stories high. It can be a way that we will very quickly expand the breadth and depth of what we're doing in healthcare to achieve, hopefully, twice the quality at twice the speed at half the cost. That's it. I appreciate your time very much.